Thanks, Steve. Can people hear me at the back? Yep, okay. So I'm going to talk about how the Keck Observatory has advanced our understanding of the Andromeda Galaxy, its system of dwarf satellites, and by proxy, other systems of comparable scale, including our own Milky Way. So this stunning image of Andromeda was kindly provided to us by Robert Gendler, and the telescopes we use to study this galaxy are seen reflecting a colorful Mauna Kea sunset in this image by Laurie Hatch. I'll give you my outline first. I think of Andromeda as the galaxy next door. There's a picture of me up there looking out my window at the galaxy next door. That's me, and that's the house next door. The house next door is close enough that we can see lots of detail in the house. We can see individual rooms in the house. We can see people running around in the house. And I'm stuck with the sad fact that I can't leave my bedroom. I've never been able to leave my room. Fortunately, my house has sort of glass walls that are sort of transparent. They're translucent, actually. You stack enough of these walls together, you can't see the rest of the house. So that's where I am. I can't see my own house that well, but I can see my neighbor's house really well. Now, don't try this at home. You could get arrested for this sort of thing. But this is what I do for a living. Now, Andromeda, to me, is three kinds of test beds rolled in one. It's certainly a test bed for studying the assembly of galaxies, and I have I believe, a little movie that goes with this is the dark matter simulation. I believe Marla showed something similar to this. This is the assembly of dark matter on scales comparable to the Milky Way or Andromeda. So Andromeda is great for seeing these processes close up right in our backyard, but it's also two other kinds of test beds rolled in one. Andromeda presents us with a set of stars that are all at the same distance from us for all practical purposes, so it's great for studying stellar populations. And some of these stars, a large fraction of these stars, their light comes to us not unimpeded. Some of their light goes through the dust and gas that's in the disk of the Andromeda Galaxy. So we can use them as probes of the interstellar dust properties. We can use them to study interstellar gas, and I'll talk about that a little bit near the very end. Most of my talk is about using it as a galaxy assembly lab. Now, the last two topics, stellar populations and interstellar medium, those actually represent a partnership between Keck and Hubble. You've heard about this partnership several times. The panchromatic Hubble Andromeda Treasury is a 900-orbit Hubble program to tile a large section of Andromeda, and putting that together with Keck Spectra has made it possible to study stellar populations and the interstellar medium. So here are some topics having to do with galaxy formation. I'm not going to cover all of them. I'll touch upon some of the ones that are underlined there. So stellar halo, the formation of stellar halos is thought to involve at least three separate processes: the accretion, or sort of merging of small galaxies. You can imagine forming a disk early on and then disrupting it through the process of mergers. It's a kicked up disk. And you can imagine things forming in situ, sort of where you see them, at least in phase space terms. Now, the dwarf satellites of the local group are, of course, important players in many of these processes. In the process of kicking up the disk, they're, of course, the very things that get accreted, so I'll talk about those. I'll talk a little bit about the unusual inner spheroid of Andromeda. This is the one aspect of Andromeda that's very different from the Milky Way. So we're interested in similarities, we're also interested in differences, and this is one major difference between Andromeda and the Milky Way. I'll talk a little bit about forensic reconstruction of individual accretion events in the halo of Andromeda. Satellite bombardment of the disk is going to be Claire Dorman's thesis. This is something we're just embarking on. I won't talk about that. And I'll talk about statistical properties of the accreted halo population. If you catch me in the halls later, you can ask me about the impending Milky Way Andromeda collision. There's no need to panic. It's going to happen a few billion years from now. And there's a simple matter that there's nowhere to run, so no panic. But I'm happy to talk about this, and also evidence of indigestion in the Milky Way itself. Satellite galaxies that it's swallowed but hasn't completely digested. I won't get into that in my talk, but we can talk about them offline. Here's a galaxy. Here's one of the luminous satellites of Andromeda, seen through the eyes of Keck. This is actually a result from Marla Jiha's PhD student, Nung Ho. This paper came out last year. The color coding, every dot is a star in this galaxy. The color coding tells you the velocity of the upper scale. Blue stars are moving towards us, relatively speaking. Red stars are moving away from us in a relative sense. And you think of this thing as being slightly elongated from the upper left to lower right. So you might think of this as a disk like that. But when you think of a disk, the axis along which a disk spins is shown over there. And really you expect the lower right to be one color and the upper left to be one color. And that's not what you see for this galaxy. So it's not a spinning disk. Instead, it's more like a spinning football. If you spin a football, if you know how to throw a football, and I don't, but if you know how to throw a football, you spin it along that axis. It's a prolate rotator, and that's how the colors should be separated if you have a spinning football, and that's exactly what this galaxy is doing. That's what this is. It's a spinning football. We think this represents a temporary stage. We think this galaxy is being transformed from possibly a gas-rich, bigger galaxy into a so-called dwarf spheroidal. But it's very interesting to catch these things in the act. So this is unusual kinematics in Andromeda 2, Andromeda 2 being the name of the satellite. There's another satellite of Andromeda I'll talk about, but this is just still talking about AND2. If you look along the major axis, where you expect to see rotation, you don't see any. Along the minor axis, you do. And the amount of rotation is rather high. This galaxy is very different from other galaxies that have a similar appearance. And this is something that's completely broken open by Keck. With Keck, without Keck, we wouldn't be able to make this diagram. This galaxy would look just like the others. It has unusual internal motions. That's what sets it apart as something that's in the process of being transformed. Here's another satellite of Andromeda. This one is a well-known satellite called M32. This is very close to Andromeda's center and has long been suspected of having had some kind of some monkey business with Andromeda. That is, it has unusual properties, and people think that it's because it's had some encounter with Andromeda. Now, we looked at this with Keck. This is a Keck spectra producing velocity dispersion, third, fourth, fifth, and sixth orders of moments of the velocity distribution. These are properties of the internal kinematics. What you see is extremely regular. Everything over here along the major axis is either anti-symmetric if it's an odd-numbered moment, like the first moment. It's symmetric if it's an even-numbered moment. Again, anti-symmetric for the third, symmetric for the fourth, anti-symmetric for the fifth, symmetric for the sixth. All of them are symmetric for the minor axis, and this is exactly what you expect for a system in equilibrium. Instead, this happens to be the galaxy closest to Andromeda. It should be the one that's all beaten up by Andromeda. Instead, here's a galaxy very far away that looks all beaten up and rotating like a football. This one looks perfectly regular. We don't know why. There's regularity when we don't expect it and irregularity when we do, but this is something we're going to try and figure out. I want to change gears a little bit and now talk about chemical abundances of individual stars in galaxies, and in particular I'm going to start the chemical abundance portion with another satellite of Andromeda called NGC 147. These stars are faint, so even with long integrations on Keck, it's difficult to see details in their spectra. Now you might look at this and say, wow, that's a lot of noise in the spectrum, and what I'll convince you in a second is these three lines are from singly ionized calcium. These are absorption lines due to calcium, but many of these small features are produced by metal lines, other elements in the atmospheres of these stars. So this is not a single spectrum, it's a co-added spectrum of about 50 similar stars in the satellite. And I'm going to run through 9 different coads, so 9 different groups of stars, and you'll see a lot of commonality to several of these weaker lines. In particular, if you focus on these 2 weak lines, they get stronger and stronger as we go to coads of different types of stars. So this is the work, remarkably, of a high school student, Lucy Cheng, who worked at Santa Cruz 2 summers. and a master student from China. And what they've done is they've put these Coedit spectra. They've been able to identify specific lines, and I show you some of these lines here. There's iron lines, there's titanium, vanadium, CN, magnesium, silicon, calcium, of course. So what Lucy did for her summer project is to take these measurements and turn them into a metallicity, an iron to hydrogen ratio. That's what you see plotted on the y-axis. And these 4 asterisks are Andromeda satellites. And what you can see is, again, perfect normalcy. Andromeda satellites resemble their Milky Way counterparts in a metallicity-luminosity relation. The Milky Way satellites that we've sampled in this particular plot are a lot less luminous than the Andromeda ones we can see, because Andromeda is further away. But we are working our way down this relation, and so far, Andromeda satellites look refreshingly normal, at least the lower luminosity satellites that you see here. All right. So these satellites, we said, are important because they get disrupted by their hosts, and these are examples of this process going on within the nearest few megaparsecs from the sun. And this is a slide courtesy of David Martinez Delgado. He specializes in studying disturbed galaxies, and in each of these cases you can see galaxies that are in the process of eating their loved ones, eating their children. I mean, I think of galaxies as farmers. They like their farm animals on and off their dining table, and this is a good example of some of these farm animals on the dining table, or rapidly being digested. Okay, here's a quick graphic of our study of Andromeda. This is the area we cover on the sky, and I'll say a few more words about that in a minute. And our Keck spectroscopic survey is very nicely complemented by an imaging survey that carried out by another group, by the Pandas group, where you can see a burnt-out view of the Andromeda Galaxy. A traditional view of the Andromeda Galaxy would actually be really tiny. That's Andromeda, the usual Andromeda we're used to, and we are studying all these fields all the way around here. And remarkably, we are working out to 165 kiloparsecs, and to our surprise, we found Andromeda stars in each and every one of these fields around this galaxy. What does that mean for the structure of the galaxy? Well, this is what it means. This is what its brightness is doing as a function of radius, and you can see 10 kiloparsecs there, 100. We're going out to almost 200 kiloparsecs. This is the work of Carrie Gilbert. Carrie Gilbert's PhD thesis was measuring the surface brightness profile of Andromeda. And one of the remarkable things she sees is not only are there stars going all the way out, their density falls off in a very regular way. And it's even more regular than this graph would suggest, because if you go to certain fields, you find that the velocity distribution of stars shows coherent clumps. These are cold clumps. Astronomers call them cold clumps, but these are coherent clumps of stars that are essentially partially digested satellite galaxies that have fallen in. So these are galaxies that have not completely been digested yet by Andromeda. If you statistically remove them, if you account for these cold components and remove them from the plot, you get a much cleaner profile. So I'm going to go back and forth a couple of times, and you can see that many of these data points move down, and you get a much tighter relationship if you remove these components than you had before. Now, there's a gray line here, because beyond that, our statistics aren't good enough to do this kind of statistical accounting for partly digested satellites. Okay. Andromeda is big because 200 kiloparsecs is radius. If you double that, you get 400 for the diameter. Andromeda is only 800 kiloparsecs away. So Andromeda is big on the sky. And out of these radii, computer simulations are able to predict what sorts of populations we are expected to see, because the problems, the traditional problems with finite resolution on these computer simulations plague their predictions close in. But in the outer parts, they predict brightness profiles that look very similar to our data. This is work of Andrea Font and collaborators, the gimmick simulations. They look very much like our Andromeda data. Again, I'll go back and forth a couple of times. And these, in fact, those blue dots are our Andromeda data plotted against their simulations. Andromeda, like I said, is big. It's really big. To quote Douglas Adams from Hitchhiker's Guide to the Galaxy, Andromeda is big. There's a familiar constellation there. I bet even the non-astronomers in the audience know this constellation. It's the Big Dipper. If you could see Andromeda, if your eyes were as powerful as Keck telescopes, you could see Andromeda, you would see something that big. That's the diameter of the Andromeda galaxy. And that brightness profile I was talking about, that's radius, so you get to double that and you get a diameter. That's it's the size of the Big Dipper. Its radius is about the size of Cassiopeia. Okay, there's very nice trend in Andromeda's halo in the sense of it becoming more and more chemically anemic as you march outwards. You can see that either in the graph on the left or the graph on the right. The outer points, the outer metallicity distributions are in red, the inner ones are in black and blue. You can see a smooth gradient in metallicity, and this can be understood quite simply. When small galaxies tend to have low metallicity, that tend to be chemically anemic. Those are the ones that preferentially get destroyed to produce the outskirts of Andromeda. It's the big satellites that can make it all the way in and populate the inner parts of the galaxy. So this chemical gradient is exactly what you expect from things like the Gimmick simulations. Here's another set of simulations. This is from Katherine Johnston and James Bullock and collaborators. One thing you expect for these satellites is from these simulations is you expect these satellites to leave trails. You can see a bunch of trails here. Some trails are bright, some trails are faint. In fact, this trail, these are images of metallicity and surface brightness. So the higher surface brightness things tend to be greenish in color, which corresponds to high metallicity. The low surface brightness things are bluish in color in this lower plot, corresponding to low metallicity. And you expect a trend between surface brightness and metallicity. That's this trend over here in the simulations. You get this trend for a simple reason. Big galaxies tend to be chemically enriched. Small satellite galaxies are not chemically enriched. So when big galaxies fall in, they leave high surface brightness trails. When small galaxies fall in, they leave low surface brightness trails. And in Andromeda, we see a trend that's very similar to what's predicted. So this is, again, giving us confidence that we understand even the properties of satellites that we can no longer see. These are dead satellites. We can do sort of a post-mortem on them as a population. I'm switching gears a little bit now. I'm going to talk about spectra of something like 11,000 red giants in the inner parts of Andromeda. This part of the Keck survey is done to complement our HST survey, the Hubble Space Telescope survey. Every dot over here is a star in Andromeda. The colors simply mean they were selected in different ways. The last two sets of colors represent selection on the basis of the Hubble data. And what we can do with this is use these data to do an unusual disentangling of Andromeda into its components. Galaxies have subcomponents, bulge, disk, and halo, and typically people use the brightness profiles of galaxies to split them up into three components. That's what's done over here, and you can see there's a lot of degeneracy when you try to make a fit like this, because you can take many combinations of these colored lines and still fit the black data points. So what we're throwing in here are constraints from stellar kinematics that tell you what the disk fraction is, and constraints from the Hubble telescope as to what the stellar luminosity function is. And this is work in progress by Claire Dorman. What we are finding out again is having velocities of individual stars gives you insight in ways that photometric data alone could never do. One of the things we've learned from this is this inner spheroid of Andromeda rotates slowly. It's mostly pressure supported. In fact, we think it's an example of a kicked up disk. You can see its rotation speed is about 50 kilometers per second. Its dispersion is about 150 kilometers per second. And so stay tuned, because this is something we're working on. I want to show you one slide on the kind of forensic reconstruction we can do for individual events, individual satellites that fell in and got destroyed. This is a map from Alan McConaughey. And what you see over here is a computer simulation that tries to mimic the basic features that's seen in Andromeda. This is a computer simulation by Mark Fardell. The different colors represent particles from a simulated satellite that fell into Andromeda. The colors actually represent different orbital phases. So the green particles haven't yet gone through Andromeda once. The red particles have gone through once and sort of peeled off to the other side beyond the minimum of the potential well. The magenta particles have swung through twice, and the blue particles have gone through pericenter 3 times. And the remarkable thing is we can identify all 3 phases of this orbit in Andromeda. The way you see these, simulations predict you should see a triangular shape in velocity radius space. What we see in our data are exactly this kind of triangular concentration. So here's another one of these shells. This particular shell represents these red particles. You can see this triangular shape caused by these shells in Andromeda. So we can carry out detailed reconstruction of streams. The last couple of minutes, I want to talk about stellar populations and ISM studies, and I'm really excited about the work of another high school student, Teresa Kraus. We're using M-giant stars to do what can best be thought of as thermometry. We're measuring temperatures of stars. We're taking their temperature, and we're trying to see if they have a fever, and I'll explain what I mean by that. If you take these stars, their spectra look very interesting. They have all these red sections here where there are sharp drops, sharp steps. Ignore this gap here. This is caused by the Earth's atmosphere. But I'm referring to these breaks. Even though there's Earth's atmosphere doing absorbing here, there's a discontinuity that's produced by titanium oxide in the atmospheres of these stars. It turns out that these TIO bands are very temperature sensitive. If the temperature is low, you get strong bands. If the temperature is high, you destroy titanium oxide as a molecule, and you don't get these bands. So you get this very nice regularity if you make a sequence of decreasing temperature, increasing B minus I color. You can see no TIO bands over here. This particular thing over here is from the Earth's atmosphere again. But the TIO bands are in these black boxes. You can see very sharp steps for cool stars and no steps at all, or weak steps for hot stars. So this is a nice thermometer. We can use this to measure the true temperatures of stars. And in particular, what we do is we fit a continuum on either side of the step, and we quantify the jump, the factor by which the spectrum jumps. This jump is strongly correlated with color or temperature, and in particular, we find stars where the spectral property of the star is exactly in tune with the observed color, and stars for which the spectral property of the star is not at all in tune with the color it has. So it has a fever. The star looks a lot redder than it should, and it's because these stars are being seen through interstellar dust. So we can use this to probe the properties of dust along individual lines of sight. This last idea here is about, again, this particular thing is a complete byproduct. Here's a spectrum of a star in Andromeda. You see night sky emission lines in this 2D spectrum. It's not bad enough that I've shown you lots of spectra. I'm even showing you a 2D spectrum. These vertical lines are produced by the Earth's atmosphere. Normally, we are using a special technique to remove them. We are using what's called non-local sky subtraction to remove them. So not all the lines go away. 5 of them survive. Turns out these 5 lines are produced by ionized gas, plasma, in the disk of Andromeda. It's produced by hydrogen, nitrogen, and sulfur, turns out. And if you measure the velocities if you measure the offsets of each of these lines from the colored line, that tells you how rapidly this plasma is spinning around in Andromeda. You get this very nice pattern. This part of Andromeda, the upper part of Andromeda, is red-shifted relative to the center of the galaxy. The lower part is blue-shifted. We're measuring the spin of Andromeda with great precision using these data. These ionized gas measurements came for free. Thank you. They came for free because they came as a byproduct of our stellar measurements. They agree really nicely with the measurements of neutral hydrogen in the same galaxy. So what you see over here, the x-axis represents our measurements, the y-axis represents measurements of the neutral hydrogen by other groups. And to summarize, the stars in Andromeda are doing this as velocity as a function of radius is doing this. That's the red line, and the pink band is the velocity dispersion. The blue line is what the ionized gas is doing. So the ionized gas is rotating more rapidly and has less dispersion than the stars. And this is, again, what you expect for big galaxies. So to summarize, I'll put up my Summary points. Our group has discovered, thanks to Keck, entirely to Keck, this vast halo around Andromeda, and to me it really calls into question whether galaxies are indeed island universes. To me, galaxies are connected at the roots. And the second thought is satellites of the local group of Milky Way and Andromeda. We can see the present satellites, but we can also say something about past satellites. The satellites are building blocks of larger galaxies, but they're also affected greatly by the proximity to the host. I talked a little bit about dissecting the structure and motion of Andromeda's components. Whoops. Just put up my summary slide again. Whoop. No, I don't want to do that. We are dissecting Andromeda's subcomponents, and finally we are measuring stellar temperature and using it as a probe of the interstellar medium, and that's where I'll stop. Thank you.